Okay, Bismillahirrahmanirrahim. Assalamualaikum. So, today in this class, we're going to start a new topic, the properties of estimator, right? So, in properties of estimator, can you mute your phone or your computer? I still hear your voice, right? So sementara ni mute dulu. Nanti you ada soalan, you unmute, you tanya soalan, right? Okay, so properties of estimator. So we have 5 properties of estimator. First is unbiased. Second is efficiency. Third is consistency and sufficiency. And the last one is minimum variance and Kramer-Rao theorem. But before we start with this topic, I just want to check, kita dah habis maximum likelihood estimator, right?
Yes.
Okay, now, so unbiased, for properties of good estimator, each estimator should be unbiased. The expected value is equal to the population parameter. So when the expected value equal to the population parameter, then the estimator is called as unbiased. And then the second estimate properties is efficiency. To get efficiency estimator, first criteria that we need to meet is the estimator should be unbiased at the first place. And then when we compare between two estimator, the estimator that has a smallest variance is going to be efficient estimator, right? And then the consistency estimator, when the limit of the variance is equal to 0, then the estimator is called as consistent estimator, right? So now, let's look at the first topic for properties of estimator, which is unbiased estimator. So theorem number 1, the statistic theta hat is said to be unbiased estimator of the parameter theta if and only if the expected value of the theta hat is equal to theta. If the expected of theta hat is not equal to theta, then theta hat is not unbiased, right? Okay, clear? Right.
Clear.
Example number 1. So if X has a binomial distribution with the parameter n and the theta, so show that the sample proportion X divided by n is unbiased estimator of theta. So to show that this estimator is unbiased estimator of the theta, right? So we need to take expected value of X, right? So the expected value of X is n theta, right? So the expected of X divided by n, this is for binomial distribution, right? So stop doing that. Right. So kita ambil expected value of X divided by n. Dan kita akan dapat expected of X divided by n, dekat luar 1 over n. Then expected of X is equal to n theta divided by n and equal to theta. So when the expected value of this X divided by n is equal to theta, then X divided by n is unbiased estimator of theta hat. Right. So now, look at example number 2. Show that unless theta is equal to half, right, the minimax estimator of the binomial parameter theta is X plus half square root of n divided by n plus square root of n is biased. So first step to check whether the estimator is unbiased, we need to take the expected value of this estimator lah. So we take expected of x plus half square root of n divided by n plus n square root of n. So kita akan dapat it's not equal to theta, right? So this is unbiased estimator lah. Are you okay, class?
Okay.
Right. Now look at example number 3.
Okay, sir, okay.
Right. Example number 3. So now kita ada satu PDF dekat sini, right? So if x1 until xn constitute a random sample from the population given by expected of exponential negative x minus delta for the x more than delta, show that x is biased estimator of delta. So to show that this x bar is biased, first we need to find the expected value of x lah. We want to take expected value of x bar. But before we take expected value of x bar, we need to know the expected value of x. Right, expected value of x is integration from delta to right, x multiplied with exponential negative x minus delta, right, with respect to x lah. So this one dapat macam mana? This one should be when you integrate, you will get 1 plus delta, right? So the expected value of x bar is equal to summation of x divided by n. So this one should be 1 divided by n and multiply with expected of 1 plus delta. 1 plus delta until 1 plus delta. Right. So this one we will not get the it's not equal to delta, right? It's going to equal to something value some value which is n 1 plus delta divided by n equal to 1 plus delta. So since expected value of x bar is not equal expected value of x bar is not equal to delta, so we can say that x bar is biased estimator. Right. Okay. So now look at another example. So in unbiased estimator, I give you a lot of example lah. Right. So just be prepared. Next week we're going to be your test number 1. So all these topic going to be in your test, right? So now look at example number 4. So let x1 until xn be a random sample from exponential distribution. So show that x bar equal to 1 over n summation of xi is unbiased estimator for theta. So the PDF for the expected value of x for exponential distribution is theta, and the variance of x for exponential distribution is I think n theta, right? Theta squared. I'm not sure, but it's okay. But we're not going to use variance. We're going to use expected value of x. So to find the expected value of x bar, it should be expected value of summation of x divided by n. This one should be 1 over n. Expected value of x1 plus x2 until xn. So this one is going to be n theta divided by n is equal to theta. So from here we know that x bar is unbiased estimator for theta. Right. Are you clear with this topic?
Yes, sir.
All right.
Yes.
Can we move on?
Yes, sir.
All right. So now look at example number 5. So in example number 5, right? So don't worry if you cannot get the note for this video. Right? I will upload this lecture on YouTube later. Right? So now look at example number 5. Let x1 until xn having an exponential distribution. Now they give us two estimator. Estimator number 1, theta 1 hat x1 plus x2 divided by 2. X2 theta 2 hat is x1 plus 2x2 divided by 3, right, for parameter theta. So the question is, are theta hat 1 and theta hat 2 unbiased? So same as before, to know whether the estimator is unbiased, we need to take expected value lah. So the expected value of x is equal to theta for exponential distribution. So now we take expected value of theta 1 hat. It should be expected value of x1 plus x2 divided by 2. So this one should be theta plus theta divided by 2. So this one should be 2 theta divided by 2. So this one to be theta. So we can say that theta 1 hat is unbiased estimator for theta. Right. So this is for the first part lah. For the second part, right, we need to take expected value of theta 2 hat equal to expected of x1 plus 2x2 divided by 3. So it's going to be expected of, going to be, the value is theta plus 2 theta divided by 3. So it becomes 3 theta divided by 3 equal to theta. So same as theta 1 hat, theta 2 hat is also unbiased estimator for theta. Right. Okay, you want more example? Or just enough?
No.
Yes.
No.
Yes.
Yes. Yes. No. Yes.
Yes, sir.
Right.
You want
Now
more?
look at the last example. I have a lot of example, but just look at the right. Example number 6. Suppose that y1 until yn are independent random variable with density function given by y power of 3 divided by 6 power of 4 exponential negative y divided by theta. Right. Y is more than 0. If you look at this PDF, right, is more likely look like gamma distribution, right? Is it?
Yes.
Gamma distribution is x power of alpha minus 1 divided by beta power of alpha gamma alpha exponential negative x divided by beta, right? For x is more than 0, beta is also more than 0, alpha is also more than 0. Right. So this one, based on the PDF, you can say that this PDF look like gamma distribution. So gamma distribution, when y having a gamma distribution, the parameter alpha and beta, right? So this one, kita boleh kata the expected value of x, the expected value of y for this distribution, expected value of y is equal to alpha beta, right? So the alpha would be, this is alpha, right? When alpha 4 minus 1 is equal to 3, and this is power 4 is alpha. So this one, it should be sorry, let me put it like this way. So this one should be 4 for alpha. Beta is going to be, beta is phi lah, right? Phi is our beta, right? And you tengok y divided by beta, right? So beta is equal to phi. So gamma distribution y. So we know that from the gamma distribution, the expected value of y should be alpha beta, should be 4 phi, right? So to know whether theta hat y bar divided by 4 is unbiased estimator for theta, right? So we use expected value of theta hat. So this one should be expected value of y bar divided by 4. So this one going to be summation of y bar divided by n for n, right? So the expected value of, this is not y bar, this is just a summation of y. So this one going to be 1 over 4n expected value of y1 plus expected value of y2 plus until expected value of yn. So this one to be 4 phi plus 4 phi plus until 4 phi divided by 4n. So now it become n 4 phi divided by 4n. So it become phi. So from the result, we can say that phi hat, which is equal to y bar divided by 4, is unbiased estimator for phi. Okay? Boleh? So now look at last example for unbiased estimator. Right. So just now we look at a continuous example. So this one is a discrete kind of example. So example number 7. So one observation is taken from a discrete random variable y, and the probability mass function of y is 1, 2, 3, right? So it's given by, so dekat sini kita ada y is 0, 1, 2, 3, 4. And this is lambda equal to 1, 2, 3. So the probability of y equal to 0 and lambda is equal to 1 is 1 over 3. Probability of y equal to 1, lambda is equal to 1, 1 over 3, and so on. Right. So from the table, how to find the maximum likelihood estimator? The maximum likelihood estimator is the maximum or is the largest probability value. So can you tell what is the largest probability value?
1 over 2.
1 over 2, right? So probability of y equal to 3 and lambda is equal to 3 is equal to 1 over 2. So this is a maximum likelihood estimator for lambda. Right. So based on the name lah, they want to find the largest probability value. Right. So the question is the estimator is unbiased? So whether y equal to 3, lambda is equal to 3, equal to 1 over 2 is unbiased estimator. Right. So to test whether the y equal to 3 and lambda is equal to 3 is unbiased estimator, we need to take the expected value of lambda equal to 3. Right. And y also equal to 3. So the expected value of lambda is lambda equal to 3 is summation of I equal to 1 until 4, right? Because y 0 until 4, y from 0 to 4, y multiply with probability of lambda is equal to 3. So now it becomes 0 multiply with 0, right? 0 multiply with 0, 1 multiply with 0, 2 multiply with 1 over 4, 3 multiply 1 over 2, and 4 multiply with 1 over 4, right? So it becomes 0 plus 2, 1 over 4 plus 3, 1 over 2, and the last one is 4, 1 over 4. So this one should be equal to how much? Can you calculate for me? Should be equal to 3, right? So since expected value of lambda equal to 3 is also equal to 3, so we can say that lambda equal to 3 is unbiased.
Yes.
Estimator. Right. Are you okay?
Yes, sir.
Yes.
So hari ni tak ada siapa nak bagi air kat I. I minum air sendiri.
Siapa nak bagi air kata you?
Ada Nescafe tu.
Nama Audi.
Right. So are you okay? Can we move to the next topic?
Yes, sir.
So
Ni ada air tu.
Sir, Nescafe sir.
mana Nescafe? Hantar sini lah. Alright. Next topic, efficiency. So it is usually possible to obtain more than one unbiased estimator. So sometimes you do a method of moment, you get unbiased estimator. When you conduct a maximal likelihood estimator method, you still get unbiased estimator, but these two estimators are different, right? So we want to know whether estimator from a method of moment and estimator from maximal likelihood, which one is better, which one is good, right? So we measure an efficiency properties, so to know which estimator is better. So now look at this one. Let theta 1 hat and theta 2 hat are unbiased estimator for the same parameter theta. So we prefer to use estimator with smaller variance. So when you have variance, the smallest variance, when you have two estimator, then you check the variance. When the variance, smaller variance is efficient, is more good than compared to another estimator. Right, now look at the theorem. Let theta 1 hat and theta 2 hat are unbiased estimator for parameter theta. If variance theta 1 hat is smaller compared to variance theta 2 hat, then we can say that theta 1 hat is more efficient compared to theta 2 hat. Right. So this is theorem number 1. This is theorem number 2 for efficient. Right. So basically the idea is we want to take the smaller variance of the estimator. Right. Now look at theorem number 2. So this is how to calculate the relative efficiency lah. Same as theorem number 1. So you need to remember relative efficiency as well in your test number 1. Right. So the relative efficiency of theta 1 hat with respect to theta 2 hat is variance of theta 2 hat divided by variance of theta 1 hat. So kita akan dapat the efficiency of theta 1 hat and theta 2 hat. So if the efficiency is more than 1, so we can say that the denominator is better unbiased estimator, which is the denominator is efficient estimator. If the efficiency less than 1, then the denominator is better unbiased compared to theta 1. So it depends. So which estimator you put as a denominator. If the theta 2 is denominator, let's say you letak dekat sini variance of theta 2 and variance of theta 1 hat. So more than 1, maksudnya theta 2 is theta 2 is efficient, right? When less than 1, theta 1 is efficient, right?
Yeah.
Now look at example number 1. So are you clear with the theorem?
Yes, sir.
Right. So look at example number 1. So let y1, y2 and y3 be a random sample from a normal distribution where both mu and sigma are unknown. Which is more efficient estimator for mu? Whether the first one or the second one. Mu1 hat 1/4 y1 until y3 or mu2 hat. So we know that yi having a normal distribution with mu and variance. Right. So to answer this question, first what we need to do is to check the unbiasedness of each estimator. So the first thing is to make sure each estimator is unbiased. So expected of mu1 hat is equal to expected of 1/4 y1 plus 1/2 y2 plus 1/4 y3. Right. So this one should be 1/4 mu plus 1/2 mu plus 1/4 mu. So this one should be equal to mu. So we can say that mu1 hat is unbiased estimator for mu, right? So this is the rule. First, before you check the efficiency, you need to make sure each estimator are unbiased. If one of the estimator are biased, then we're going to consider on unbiased estimator only, right? And the second one is expected of mu2 hat. So this one should be expected of 1/3 y1 plus 1/3 y2.
Oh my god, it's so cool.
1/3 y3.
Don't show me a video. I can't see it. Or do you want me to hit someone?
Yes.
Sedap.
Siapa cakap?
Sorry sir, sambung. Saya.
Oh shit.
Right. So this one should be 1/3 mu plus 1/2 mu plus 1/3 mu. So this one should be equal to mu, right? So we can say that mu2 hat is also unbiased estimator for mu, right? So then the next step is to check the variance for each estimator lah. So we need to check variance for each estimator. So the first one is variance mu1 hat, right? So this one should be variance 1/4 plus, variance 1/4 y1, right? y1 plus 1/2 y2 plus 1/4 y3, right? So this one should be 1/16 variance of y1 plus 1 over 4 variance of y2 plus 1 over 16 variance of y3. So this one 1 over 16 sigma squared plus 1 over 4 sigma squared plus 1 over 16 sigma squared. So this one should be berapa ni? How much you get? Can you calculate for me?
0.375.
0.375 sigma squared.
Sir.
Right. The second one is variance mu 2 hat. It should be variance 1 over 3 y1 plus 1 over 3 y2 plus 1 over 3 y3. Right, so this one should be 1 over 9 variance of y1, 1 over 9 variance of y2 plus 1 over 9 variance of y3. Right, so this one should be berapa ni? 1 over 9 sigma squared plus 1 over 9 sigma squared plus 1 over 9 sigma squared. So this one should be equal to
3 over 9.
3 over 9. 3 over 9 sigma squared. So this one kalau fraction berapa? It should be 3 over 8 sigma squared. So which one is smaller? 3 over 8 or 3 over 9?
3 over 9.
3 over 9 is smaller lah.
Smaller.
So 3 over 9 variance of mu 2 hat is smaller than variance of mu 1 hat. So we can say that mu 1 hat, mu 2 hat, this is the smallest one kan, is efficient estimator for mu. Okay?
Estimator for me.
Right.
Benar tu.
So another way to show whether the efficiency by using relative efficiency in theorem number 2, right? Theorem number 2, we measure relative efficiency by taking the proportion between variance estimator number 2 divided by variance estimator number 1, right? So this one should be variance of mu 2 hat divided by variance of mu 1 hat. So this one should be 3 over 9 sigma squared divided by 3 over 8 sigma squared. So this one sama dengan berapa? What is the value here? What is the value?
8 over 9. 8 over 9.
8 over 9. 8 over 9 is less than 1 kan?
Yes, sir. Yes.
If frequency efficiency is less than 1, then the nominator is better unbiased estimator. So we can say that the same conclusion lah. So efficiency mu 1 and mu 2 is less than 1. So mu 2 hat is efficient estimator.
3 over 9 divided by 3 over 8.
Right? Okay?
Okay.
Can you solve example number 2 for me?
Yes, sir. You can do it.
Right.
Alright, sir, let's go.
So example number 2, right? X1, X2 until X4 is be a random sample from a population with mean equal to mu and variance equal to sigma squared. So given X and T are unbiased estimator. So this is S and T are unbiased estimator. So we want to identify which estimator are efficient estimator for mu. So first step is we need to find the variance of S and variance for T, right? So variance for S is variance of X bar, which is also equal to variance of summation of X divided by N. So this one should be 1 over N squared variance
Sigma square.
sigma, sigma squared, right?
Yeah.
So sigma squared plus until sigma squared, because this is sigma squared number 4. This is sigma squared number 1, and this is sigma squared number 4,
4.
right? And suppose N is equal to 4, right? So this one going to be sigma 4 sigma squared divided by 4 power of 2. Okay. So this one should be equal to sigma squared over 4. So this is the first variance for S. And variance for T is equal to variance 2x1 plus minus 3 over 4x3 plus 1 over 3x4. Right. So this one should be 4 variance x1. This is minus, right? So minus from variance going to be plus. This is going to be 9 over 16 variance x3 plus 1 over 9 variance x4. Right. So this one should be 4 sigma squared plus 9 over 16 sigma squared plus 1 over 9 sigma squared. So this one going to be berapa ni? How much? If you solve this one, what is the value?
Pak Jilai.
4.6736.
In fraction berapa?
673 over 144.
Berapa fraction
Fraction dia 673 over 144.
3 over 144.
673 over 144.
Can you calculate betul-betul? This one should be berapa ni? 3 over 1?
37 over 8.
73.
6, 7?
601.
601. Yang mana tu ni?
673.
673.
6, 7?
3.
73, sir.
673.
Yes.
Yeah.
Over
Over
144.
144. Variance. Is it?
Yes.
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 Yes, sir.
So which one is smaller? 1 over 4 or 673 144?
1 over 4.
It should be
1
1
over
over 4 lah. Right. So we can say that S is efficient estimator for me.
If online class does not work, sir. Kenapa tak buat?
Right?
Alright.
Okay, dah habis salin? Nak salin lagi ke?
Dah, sir.
Tak nak. Dah boleh dah. Dah.
Right. So this one, I put it example number 3 ni. You buat sebagai you punya flip grid. Right. Solve this one.
Okay, sir.
As your flip grid.
Better.
Okay. Dah salin dah?
Sekejap. Sikit lagi.
Dah sir, dah.
Right. So the next topic is minimum variance estimator, the Kramer rule, lower bound. Right. So now tadi kita dah tengok the efficiency estimator. So in efficiency estimator, the requirement is first the estimator should be unbiased, and then to claim the efficient estimator, the variance for that estimator should be the smallest variance among compared to others, right? So now in minimum variance estimator, the Kramer rule lower bound, given two estimator, theta 1 hat and theta 2 hat are unbiased, right? We know that from prior knowledge the estimator is efficient. The best estimator is a smaller variance. But the question is how good the theta 1 hat and how good the theta 2 hat, or is there any other estimator available, right? To answer this question, we need to use Kramer rule lower bound techniques, lower bound. So theorem number 1, if theta hat is unbiased estimator for theta, and the variance of theta hat is equal to 1 divided by n expected of differentiation between ln fx with respect to d theta and taking the square root. Kalau this value sama dengan the variance of theta hat, then theta hat is a minimum variance unbiased estimator. Right. If not equal, then the theta hat is not minimum variance unbiased estimator. So another theorem, theorem number 2, it is assumed that the PDF of Px satisfy the regularity condition, right? Let's say kita tengok the expected value of the derivative of ln fx with respect to theta is equal to 0. When the expected value of this value is equal to 0, then baru you akan pakai this formula. Variance of theta hat more than or equal to 1 divided by negative n expected of second derivative of ln fx. So this is a two different formula, right? So the key is when the expected value of derivative ln fx is equal to 0, then baru you pakai this formula. If the expected value of the derivative ln fx is not equal to 0, use this formula. Right, let's say I letak this one expected of, this one I letak sebagai phi yang panjang kan. If phi is equal to 0, use theorem 2. If theorem number 1. Yeah, theorem number 2 betul. Right, if phi is not equal to 0, use theorem 1.
1.
Right. So now look at example. Right. So show that X bar is minimum variance unbiased estimator of mean mu of the normal population. Right. So normal population, the PDF for normal population, is Fx mu variance equal to 1 divided by 2 pi sigma squared square root, right, exponential negative 1 over 2 x minus mu divided by sigma and d squared, right? For x, of course, from negative infinity to infinity, right? So from here, we know that the expected value of x is equal to mu, and the variance of x is equal to sigma squared, right? So the formula, first kita tengok yang first one. The formula, dalam formula ni kita nak tengok the ln of fx. So what is the ln of fx? Kita cari ln fx. Ln fx. So ln 1 over 2 pi sigma square root exponential negative 1 over 2 x minus mu divided by sigma square. So this one jadi macam mana? Ln 1 minus ln 2 pi sigma squared over half minus 1 over 2, right, x minus mu divided by sigma squared ln e, right? So dekat sini kalau tengok sini, this is 0 and this is 1, right? Apa yang tinggal dekat kita adalah negative ln 2 pi sigma squared 1 over 2, right? So this one minus 1 over 2 x minus mu divided by sigma squared. Kita boleh pecah lagi tak? Can we
Boleh kot.
separate more?
1 over
So it become negative ln sigma squared, this is sigma saja, minus ln 2 pi
Pi.
of half. And this one should be minus 1 over 2 x minus mu divided by sigma squared.
Square.
So now the second step is we want to take the derivative of ln fx with respect to mu. Right. So this one should be, this one tak ada apalah, ni kosong. Dan dia akan tinggal kita 1 over 2 x minus mu divided by sigma. This is the whole bracket. So 2 minus 1, and so dia akan jadi sini negative. Kita kata 2 negative 1. Right. We differentiate dalam sekali. Right. 2 minus 1, 2 dekat sini, negative 1 dalam. Right. So it become x minus mu divided by sigma. Right. So this is for second step. So now look at that formula. If expected value of ln fx divided by theta with respect to theta is equal to 0, then use the second theorem. If not equal to 0, use the first theorem. Right. So the expected value of this one should be equal to berapa? Should be equal to 0 juga kan? Betul?
Yes, sir.
Right.
Zero.
But don't forget, this one ada kuasa 2 dekat sini kan. Bila kita buat, kita buang dekat atas saja dan bawah ni still ada kuasa 2 kan. This is power of 2. Right. So kalau kita pecahkan this one, kita akan dapat x minus mu divided by sigma multiply with 1 over sigma. So sama saja kan? Right, sebab I nak kekalkan dia dalam bentuk standard normal. Right, selalu kita letak kita punya distribution, make sure kita kenal distribution tu. Right. And then step number 3, what we need to do is to take the exponential, the expected value of derivative of ln fx with respect to mu. I use theorem number 1. I think theorem number 1 also work for this example, right? So this one should be the expected value of x minus mu divided by sigma, and then multiply with 1 over sigma, and then square the expected value, right? So this one should be the expected value of x minus mu is expected value of x minus mu squared is equal to sigma, right? Sigma squared. So this is based on theorem. Sorry, this is based on the second moment.
Buat the mean.
Moment about the mean, right? So from here kita tahu sigma squared divided by sigma, right? Multiply with 1 over sigma squared. Then this one is squared juga kan? Betul tak? This one squared, squared, right? So it become 1 over sigma squared. Is it? Can you get it? Right?
Yes.
So now we input into the whole formula 1 divided by the expected value of d ln fx, right? Divided by with respect to mu, and this is square, right? So it become 1 over n multiply with 1 over sigma squared. So it become sigma squared over n. Right. So the variance of mu hat, which is also equal to variance of x bar, is equal to variance summation of x divided by n. Right. So this one should be, if you expand based on theorem, this is based on theorem number 1, chapter number 1, right? If you still remember, it will become sigma squared divided by n, right? So since variance of x bar is equal to 1 divided by n expected of the derivative of ln fx with respect to mu squared, so we can say that mu hat is minimum variance unbiased estimator for mu. That's all. Are you okay?
Okay.
Any questions so far?
Sir, no question.
No, sir.
Right. Now we look at example number 2. Right. Example number 2 show that the mean of a random sample of size n from exponential population is MVUE of parameter theta. Right. So this is from exponential distribution. The PDF for exponential distribution with the parameter theta is 1 divided by theta exponential negative x divided by theta for x is more than 0. Then the expected value of x should be equal to theta, and the variance of x should be equal to theta squared. Right. And the variance of x bar is equal to theta squared over n. Right? So for the first step, what we need to do is to find the ln of fx. So ln fx is ln 1 over theta exponential negative x divided by theta. Right. So this one should be equal to ln 1 minus ln theta minus x divided by theta ln exponential. Right. So this one should be equal to 0 and this one should be equal to 1. So apa yang kita tinggal? Negative ln theta minus x divided by theta. Right. So the next step is we need to find the derivative of ln fx with respect to theta. Right. So this one should be negative 1 over theta plus x divided by theta squared. Right. So make it nicer. X divided by theta squared minus 1 over theta. Okay. So this is the derivative of ln fx with respect to theta. Right. So if you look at the expected value of derivative ln fx with respect to theta, right? So this one should be equal to expected of x divided by theta minus theta squared minus 1 over theta. So this one should be theta over theta squared minus 1 divided by theta. So this one sama dengan berapa ni? This is for just for checking whether you want to use theorem number 1 or theorem number 2. Right. So ini sama dengan berapa? What is the value here? Theta divided by should be equal to 0. Right. So since expected of derivative ln fx with respect to theta is equal to 0, then we can use theorem number 2. Right. So theorem number 2 says that we need to do extra derivative, second derivative. Right. So d squared ln fx divided by d theta squared. So this one should be berapa? With respect to theta, right? So it become negative 2x divided by theta power of 3 minus plus 1 over theta squared. So this is a second derivative. So the fourth step is we need to take the exponential second derivative. So this one should be expected of negative 2x minus divided by theta power of 3 plus 1 over theta power of 2. Right. So this one should be negative 2 theta divided by theta power of 3 plus 1 over theta power of 2. Right. So this one sama dengan berapa ni? What is the value here? It should be negative 2 plus 1. It should be negative theta divided by theta power of 3. And then become 1 over theta power of 2. Right. So the next step is step number 5. We use the complete formula, negative n expected of d squared ln fx with respect to d theta. Right. So become 1 over negative n multiply with 1, multiply with negative 1 over theta squared. So it become theta squared over n. So since variance of x bar is equal to 1 over negative n exponential d squared ln fx with respect to theta squared. So we can say that x bar is minimum variance unbiased estimator for theta. That's all. Okay? Boleh? Any questions so far?
Boleh sir, boleh.
Right.
No sir.
No?
No.
Which one?
Sir, enough, sir.
You don't want an example anymore? Okay. All right. Example number 3, you do it by yourself. Put it into flip grip by today and by tomorrow. Right? So you explain example number 3 and before this ada satu lagi example, 2 example you explain dalam flip grip. Alright. So the last topic, sorry, yeah, this is not the last topic. This is the second last topic. Is sufficient estimator, right? If the estimator utilize all information in sample relevant to estimator of theta, right? So look at the theorem number 1. This is theorem for a sufficient estimator. So in this theorem says that to indicate the estimator is sufficient, we need to take the likelihood function of the PDF and try to factor the likelihood function. If you can factor the likelihood function into 2 parts, which is the first one is the variable and the second part is the parameter, then we can say that the estimator is sufficient. That's all. Right. So now look at this example. So let x1 until xn be a normal distribution with mu is equal to theta and variance equal to 1. Let S is equal to summation of x and S is sufficient estimator of theta, for theta. Right. So first step, what we need to do is we need to find the function of the PDF function for normal distribution. So the PDF function for normal distribution is 2 pi sigma squared, right? Exponential negative 1 over 2 x minus mu divided by sigma and u squared. Since we replace the mu value into theta, so it become 2 pi and the variance equal to 1, right? Variance equal to 1. Exponential negative 1 over 2 x minus theta divided by 1 square. Right, so divided by 1 kita tak payah letak lah. So no need to put. Right. So next, we need to find the likelihood function of mu n of the theta, right? The theta. So you only have theta, right? So it become f x1 theta multiply with f x2 theta, not plus, multiply until f x n theta, right? So you remember next week is your test number 1. Semua topik ni masuk dalam test number 1. right? So it become 1 over 2 pi square root, right? This is power of n exponential negative 1 over 2, and then this one going to be summation of xi minus theta squared. So if we expand this function, right, it will become xi x minus theta x minus theta. So it become x power of 2 minus 2x theta plus theta squared, right? So kita buat macam ni, 2 pi square root, this is power of n, since we take the likelihood function, exponential negative 1 over 2 x square, don't forget the summation, x square minus summation of 2x theta plus n theta squared, right? So to know whether this estimator is sufficient, we need to do a factor. We need to factor the function into two parts. First is only the parameter, and another one is others value, the constant, right? So it become 1 over 2 pi, right? Power of n exponential. This one kita bawa semua yang bukan parameter letak tepi. So kita bawa yang parameter saja. 1 over 2 summation of x square. And then this is multiply exponential negative this is negative summation of x theta, and this is going to be minus, this is plus minus n theta squared divided by 2, right? So this one, the value of negative value kan. So this is the first part without the parameter, and this is the second part with the parameter. This is q theta, this is h xi, right? So since we can factor this likelihood function, so we can say that theta hat is sufficient estimator for theta, right? Are you okay?
So what is the difference between sufficient estimator and efficient estimator?
Sufficient estimator means we can factor the likelihood function. The efficient estimator means we want to compare between two estimator, and we choose the estimator with the smallest variance. When we got the smallest variance estimator, then it's going to be efficient, right?
Okay, understood. Thank you, sir.
Right. Now, example number 2 for a sufficient estimator. Now look at example number 2. Let x1 until xn be a Poisson distribution with lambda parameter, and S is equal to summation of xi. So the question is S sufficient estimator for lambda? So to do this, we need to know the PDF function for Poisson distribution. So what is the PDF function for Poisson distribution? Fx lambda is equal to exponential negative lambda, and then this is lambda power of x divided by x factorial. And then the first step to find whether this estimator is sufficient, we need to take the likelihood function of the Poisson distribution. So it becomes exponential negative n lambda power of summation of x I divided by the product of xi factorial. So now if we can factor this function into variable and the parameter, then this estimator is sufficient. So we put the the parameter on one side. Let's say, I letak this is the variable, the constant, one side. Another one is negative n lambda summation of xi. So this one is hx, and this is q lambda. So since we can factor this, so it become, so we can conclude that lambda hat is, or no, not lambda hat, the s is summation of xi is sufficient estimator for lambda. Okay? Do you understand?
Understood, sir.
Right. Good. So now we try to do to look at the last topic for properties of good estimator. So the last topic for good estimator is consistency. Means we want each estimator to be consistent, right? When we do a prediction, we do the estimation, we want the estimator to be consistent. So consistency says that an unbiased estimator theta hat for theta parameter theta is consistent estimator if and only if the limit of the variance when n approaching to infinity is equal to 0, right? So we need to test the variance of theta hat with limit n approaching to infinity should be equal to 0, right? Itu saja, right? So kalau dia tak sama dengan kosong, then it's not consistent. So now look at example number 1. So show that p hat equal to x divided by n is a binomial of a binomial distribution, is a consistent estimator of parameter p. So first step is we need to find the variance of p hat, right? So, but from the binomial distribution, we know that the expected of x is equal to np, and the variance of x is equal to npq, right? So this is the information that we have from a binomial distribution, right? So next we need to find the variance of p hat to prove whether this estimator is consistent. The variance of p hat is equal to variance of x divided by n. So this one should be equal to npq divided by n, should be n squared, right? Should be equal to pq over n. So this is the variance of p hat. So next step, this is the first step. Second step, and the third step is we need to find the limit n approaching to infinity for the variance of p hat. It should be equal to 0, right? So limit n approaching to infinity, pq divided by n is equal to 0. When the limit of variance equal to 0, then we can conclude that the p hat is consistent estimator for p, right? Are you okay? Is there any question? Do you have any question? Do you have any question?
No.
No. Right. So one last example, right, for consistency.
No, sir.
Example 2.
Pak An struggle.
Right. So let x1 until xn denote a random sample from population with PDF 1 over 6 pi exponential negative 1 over 6 x minus mu squared for x between negative infinity to infinity. So its estimator mu is consistent estimator for parameter mu, right? So mu hat here, mu hat is consistent estimator for parameter mu. So to find that, we need to find the expected of mu hat, which is also equal to expected of x bar. This is based on the last topic that we have learned, so which is also equal to mu, right? So this is, we confirm that mu is unbiased estimator, right, for mu. So to test whether this estimator is consistent, first we need to make sure this estimator is unbiased estimator, right? Second step is we need to find the variance of mu. This one should be variance of x bar is also equal to 1 over n multiplied with sigma squared, right? Right. So the limit of n approaching to infinity for 1 over n sigma squared is equal to 0, right? So we can say that mu hat is consistent estimator for mu. I think that's all for this topic. So I have another video on consistent estimator for sample variance on normal distribution. You can look at into my YouTube channel. I letak dalam satu video 3 tahun lepas. So you boleh tengok dalam video tu. It's quite long. I just don't want to explain here. Just watch the video. How to solve how to show that the sample variance from a normal distribution is consistent estimator. So I think that's all for estimation topic for properties of good estimator. So we will continue our lecture on the next class on interval estimation. But before we end our lecture, just to remind, next week on what day you want? On Monday. Monday, I want to conduct test number 1 for group A, and Tuesday test number 2 for group B. Alright. So the topic that we'll cover on test number 1 and test number 2 is topic chapter number 1 and chapter number 2 until what we have learned today.
Okay.
Right? So there are 4 questions.
Test what time?
What time in our class time?
Alright.
On Monday.
Monday. You like Monday?
I
No.
like Thursday.
Oh,
Wednesday.
Expand.
So better be prepared whether I want to do on Monday or Tuesday or Wednesday or Thursday. Suka hati.
Sir, we give you coffee, sir.
Wednesday.
Thursday.
Friday.
Friday, sir.
Alright.
Friday we free.
So just be prepared. Right. Just be prepared.
Okay.
Do you have any questions so far?
How many questions? The test.
4 questions.
4 questions, alright.
We give
One
you coffee.
question,
okay?
how many marks?
Each 10 marks.
Oh,
Okay.
How many marks?
okay, sir.
One question, 10 marks.
Language, please.
Alright.
Keep my language, okay?
Okay.
Come on.
Azimah.
Okay then. Ada soalan tak? Do you have any question?
Tak ada, sir.
So then I think that's all. Thank you. Assalamualaikum.
Thank you, sir.
Thank you, sir.
Bye.
Saya datang.
I will get you a coffee.